linear algebra by talking about systems of linear equations. A system of linear equations has the following general form. There are multiple equations. Each one has the form a11x1 plus a12x2, etc., plus a1nxn equals b1. In general, we're going to have n unknowns, xn's, and we'll have m equations. Any set of values x1 through xn that satisfy all of these equations is called a solution to the system of equations. In general, for a real valued system of linear equations, we obtain either no, exactly one, or infinitely many solutions. In a system of linear equations with two variables, x1 and x2, each linear equation defines a line on the x1, x2 plane. Since a solution to a system of linear equations must satisfy all equations simultaneously, the solution set is the intersection of these two lines. The intersection can be a line if the two lines are identical. It can be a point, as in the diagram here, which is the point of the intersection of the two lines, or it can be empty in the event that our two lines are parallel and unequal. In this illustration, we're given the system of equations 4x1 plus 4x2 equals 5 and 2x1 plus 4x2 equals 1. The solution space is the ordered pair 1, 1/4. Similarly, for three variables, each linear equation determines a plane in the three-dimensional space. When we intersect these planes, that is, satisfy all linear equations at the same time, we can obtain a solution set that is a plane, a line, a point, or empty. As an example, consider the system of equations x1 plus x2 plus x3 equals 3, x1 minus x2 plus 2x3 equals 2, and x2 plus x3 equals 2. This system has a single solution, 1, 1, 1. Because it has only that one solution, we call the solution unique. Here's a slightly different set of equations. Here our last equation is switched to 2x1 plus 3x3. This is a system of equations with no solution. You can see this because if you add the first two equations together, you end up with 2x1 plus 3x3 equals 5. And we can't possibly have 2x1 plus 3x3 equal 5, while at the same time having 2x1 plus 3x3 equals 1. We make one final adjustment here and change our last equation to 2x1 plus 3x3 equals 5. This system now has infinitely many solutions. If we add the first equation to the second equation, we get 2x1 plus 3x3 equals 5, which makes the third equation redundant. And so ultimately, we really do have a relationship between two equations rather than three. For this set of solutions, we parameterize. We set x3 equal to t, and given that, a solution set will be given by 5 halves minus 3 halves t for x, x1, a half plus 1 over 2t for x2, and t for x3. Any solution of this type will work as long as t is a real number. We'll see how to create solutions and solve system equations like these as we move forward. For a systematic approach to solving systems of linear equations, we will introduce a useful compact notation. We have a system of equations. We collect all of the aij coefficients and form them into vectors. So our more compact form is x1 times the vector a11 all the way down to an1 plus x2 times a12 all the way down to an2, etc. plus xn times a1n all the way down to ann is equal to b1 through bn. An even more compact form is when we take the vectors of coefficients, put them together as a matrix, multiply by a vector of x's, and make that equal to our vector of constants. In the next video, we'll have a close look at these matrices and define some computation rules. Then we'll take on the problem of solving these linear equations.